Hi, it's James. This is problem 3 from homework 9. It involves motional EMF. You have two bars that are both moving, and so you have two loops uh, in which current can be induced. And as a result of the motion of the two bars, the area enclosed by the two loops is increasing. And so we'll see what current that produces in this resistor in the center. To do that, I'm just going to quickly derive the expression for motional EMF. Remember, Faraday's law says that EMF is minus number of turns of wire times the derivative of the flux with respect to time. I'm going to consider the case in which there's just one loop. And so n is 1, so we get minus 1. The flux is the B field times the area enclosed by the loop times cosine of the angle between the B field and the normal to the area enclosed by the loop. And so I get minus the B field in these motional EMF problems is constant, so I can bring it out of the derivative. The angle between the B field and the normal to the area is 0 degrees. I'm going to select the direction of the normal to the area to be into the page rather than out of the page. So if the normal to the area is into the page, it's parallel to the B field, and so theta is 0. So this is just 1. So because cosine of 0 is 1, and so I get dA dt. And the area is given by the length, which I'm going to make a variable. I'm going to call the length x, and times this, which is actually this is usually called the length, I guess, and this I'll call the width. I'll call it x in any case. So this is minus b. The area is L times x. It's L times x. So derivative of Lx with respect to time. And L is constant. The bar isn't getting any longer. So it's minus BL dx dt. And dx dt is just, if you remember from physics 1, dx dt is velocity. So minus BLV is the EMF. And the magnitude of that is just BLV. Okay. So sorry for the sharp cut. I decided to redo the solution to the problem. So in this problem, we have the area of the right loop increasing as the right bar goes to the right, and the area of the left loop increasing as the left bar goes to the left. Now we have the expression from the first part of this solution, the EMF equals BLV. And the sense of the EMF on the right side is given by the right-hand rule. So the B field is into the page. The flux is increasing associated with that B field because the area is increasing. So the loop wants to create a B field in the opposite direction to oppose that increase in the flux. So for the right loop, the B field produced is out of the page, produced by the induced current is out of the page. And so my thumb is out of the page, my fingers curl counterclockwise. So the current on the right part is going to go like this. It's going to go counterclockwise. Call that I right. Likewise, the same thing is happening in the left loop. The flux due to the B field into the page is increasing. So the left loop wants to produce a current that would produce a B field out of the page to oppose the increase in flux into the page. And so with my thumb out of the page, my fingers curl counterclockwise just as before. So the current on the left side is also going counterclockwise. And in the middle, we're going to have a current which I'll choose to be going up, call it I middle. If I've chosen it to be in the wrong direction, I'll get a negative value for I middle. And so you can see that the I right tends to decrease I middle because I right would go down in the middle part. And I left tends to increase I middle because I left would go up in the middle part. That's the effect of the right loop being to the right of the middle part and the left loop being to the left of the middle part. Okay, so now I want to figure out the answer to the question, which is the magnitude and direction of the current I middle. I want to figure out what I middle is. So it's basically a problem from earlier in the course in which we use Kirchoff's laws. So the circuit that I can draw to represent this situation is like this. I'm going to draw everything the same, except I'm going to use batteries to represent the EMFs produced due to the change in area on the right and the change in area on the left. So the EMF on the right tends to make the current go round counterclockwise. So it has a positive side on the left because the current's going to the left in this top portion. And this bar I can represent as a resistor with resistance R right. And pretty much the same thing on the other side, except, yeah, pretty much the same on the other side. The I left is going counterclockwise, so the battery representing EMF left, so this is EMF right, this is EMF left. The battery representing EMF left has the positive side on the left, so that the current will go counterclockwise. And here's the resistance of the bar on the left. Okay, so this is just a Kirchoff's laws problem. And we put in the currents. So I right goes like this. I left goes like this. And I middle goes like this. And so if I look at, remember the junction rule, if I look at this junction, I have sum of currents in to the junction equals sum of currents out of the junction. And that equation is I middle is going in, I right is going in to that junction. So I middle plus I right is equal to the currents coming out, which is just I left. So that's my first equation. The next two equations that I'm going to use to solve for, I need three equations to solve for the three unknowns, I left, I middle, I right. The next equation is a loop rule equation. I'll choose the right loop for this equation. So I'll start here and go clockwise, say. And so I come up here, I go through this resistor in the direction of the current I middle. So I have I middle R with a minus sign because I'm going in the direction of the current. It's a voltage drop. I keep going clockwise. I'm going down from positive to negative, down by ER, so minus or EMF R. And then I go through the resistor RR against the current IR, right? The current IR is going counterclockwise, so it's going up through RR. I'm going against it, so I'm going, so that'll be plus IR, RR. And I come back to where I started, so the total of all of that has to be 0. And the third equation, I'll choose the left loop. I'll just make sure I did this correctly. I went through this resistor in the direction of the current, so minus, from positive to negative, so minus, and against the current, so plus. Yeah. So equation 3, I'll start here and go clockwise. It doesn't matter which way I choose to go or where I start. So I'll go through here. I'm going against the current. I left. So I'm going to go, I'm going to have a term plus I left, R left. I'm going from positive to negative because I'm going clockwise. I'm going like this. So I'm going down, so minus EMF left. And then I'm going against the current in the middle, so plus I middle R. And that brings me back to where I started, so that equals 0. And I want to solve for I middle, so I will pause for a second and strategize, and I'll come back. So I decided to solve 1 for I left. Well, it's already solved for I left, so plug I left into 3. That'll give me an equation with I right and I middle. Solve for I right in terms of I middle, plug into 2, and that'll give me an equation for I middle, which I can solve to give me what I'm looking for. So let's see if that works. Or, if I do that correctly, rather. So I left goes in here, so 1 into 3, and I left is I middle plus I right, so we get I middle plus I right. And by the way, this is just algebra, so if you want, you can skip to the end and see how this comes out. Times R left minus EMF left plus I middle R equals 0. And I want to solve for I right. So if I can bring everything over to the other side, which will leave just I right RL. So I'm going to wind up with I right being, when I divide by RL, I'll get a 1 over RL times everything else here brought to the right. So minus EMFL becomes plus EMFL on the right. Plus this becomes minus I middle R on the right. And I middle plus I middle R left becomes minus I middle R left on the right. And yeah, looks good. And then I plug this into 2. And I get, so this is I right, I'm going to plug it in there. So I wind up with minus I middle right, I'm just rewriting equation 2, minus EMF right plus, and I plug I right in there, so it's R right over R left times all of this EMF left minus I middle right minus, in fact, this is minus I middle times R plus RL, so I'll do that, R plus RL, good, and all of that equals 0 because that's equation 2. And so I wind up with, I want to get I middle by itself, so I'll move everything else to the right. So I wind up with I middle times It's a good thing to write legibly so you know what you've written later. I middle times minus r, and then RR over RL times a minus, so minus RR over RL. I'm doing this a little bit fast, so times R plus RL. Good. And then I move everything else to the right, so minus EMFR becomes plus EMFR plus EMFL times this ratio becomes minus EMFL times RR over RL. So I get that I middle equal to this thing, EMFR minus EMFL RR over RL over all of this. Notice that I've got do I want to simplify it all? No, I'll just, so this is minus R minus RR over RL, R plus RL, good. And then I'll plug in numbers, and so EMFR, the right EMF is remember EMF is BLV, and so it's the right EMF is BLV right minus EMF left is BLV left, and then RR over RL over all of this minus R minus RR over RL, R plus RL, and now I should be able to plug in. Okay. So I get B is 0.01 Tesla. So I've got 0.01 Tesla. And I've got B and L in both of those terms. So I'll do B times L. L is the distance between the rails, and so that's the 11 centimeters, so 0.11 meters. And so yeah, BL times VR, the right velocity, looking at the picture, is 2 meters per second. Minus the left velocity is 4 meters per second. Times the ratio R right over R left. R right from the picture is 15 ohms, which makes R left 14.5 ohms. So 15 ohms over 14.5 ohms divided by minus, I'll take the minus, minus R. R is the middle resistor, so that's 5 ohms. Minus R right over R left, again 15 over 14.5 times R plus R left, 5 ohms plus R left is the 14.5 ohms. And perhaps I have not made an algebra error. I'll pause, plug into my calculator, and see if I get the approved answer. And yes, it came out all right, so I didn't have to redo all that algebra. No, I mean, it's not it's most of a page of algebra, so it's good to be confident at doing algebra, but no matter how much algebra you've done, you will make mistakes. So just be aware of that. Don't worry about it. If you're doing something important, assume you have a mistake and you know, do it again. Check your answer. It's the tedious part of this for if you enjoy the physics. So anyway, then that's how it comes out. The point of this problem is that because the area on the right and the area on the left are increasing, you get currents that go, and the B field is into the page, you get currents that go counterclockwise, which means that one of them is going down in the middle, the other one is going up in the middle. So they tend to cancel, but they don't cancel completely. Instead, you get this small current in the middle. And I'll leave with the numbers for the problem so that you can refer to them if you want to think about this. Okay, well, thank you for your time, and hope this was of use, and have a good day. Just a quick postscript to the problem. Here is the information written out a little bit more clearly, and the direction of the current. Notice that the answer is positive for I middle, meaning that the current is going up in this diagram through resistor through the resistor with resistance R. So this is direction is up. If the answer had been negative, then the direction of the current would have been in the direction opposite the one I chose for I middle. But because the answer is positive, that means that the current is in the direction I chose for I middle. So direction is up. All right. Thanks again. Have a good day.